Excellent. All right, next up we have Anish talking about teaching modern EDA. Go away, Anish.
Well, I'm Anish. I'm an undergrad, final year undergrad at Carnegie Mellon University, and I've been involved with this teaching initiative for the past 2 years. We're trying to kind of use open source to better teach modern EDA tools to electrical engineering students. So we'll talk about kind of why is this interesting? Why are we running a course based on open source EDA? How do we structure the course to optimize for learning outcomes? And kind of how do we design different assignments that the students get the most out of? Some of the student tape-out projects we've seen and how we make this course around the tape-out, and then some challenges we've hit and opportunities for improvement, and kind of how you can use this, how this can be expanded out to other institutions. So we'll start with looking at the kind of the motivation behind this. So as hopefully everyone here is familiar with, in 2020, the release of the Skywater 130 PDK and some interest from industry made it feasible to tape out chips, fully open source flows, open source designs, open source processes. This, combined with general interest from the industry into improving VLSI education, our department has had a lot of interest from different companies in kind of producing better VLSI students coming straight out of undergrad. And one of the things that we've kind of noticed is the core educational value is often a little bit bogged down when you're also dealing with the inefficiencies of industry tools. Everyone's probably familiar with a lot of these tools. Not necessarily the most user-friendly, especially the first time you're learning them, and trying to teach students about how things work under the hood, having to first deal with the interface of the tool, kind of hiding what's actually going on, can be tricky and can be discouraging at times. And why has this become practical now? Well, partially because a lot of these tools have become so readily accessible. The release of the open PDKs and the MPW tapeouts means that the open lane flow and similar flows have become fully RTL to GDS viable, and that they can actually be used to produce silicon. And the other thing is the access to cheap and easy tapeouts, such as Matt Venn's Tiny Tapeout program, which I think there's talk about that later. But general idea is for 150 bucks, you can get a few thousand cells worth of space on a shared multi-project chip and scale up from there, including getting silicon back. And then Chip Ignite, which is eFabless's program, where for 10K you can get full chip worth of area, and that includes packaging, fabrication, and all of that. And having access to this means that we can start to build a course around this and allow students to have this tape-out opportunity at a very reasonable scale. So how did this course start up? Originally, I just wanted to get people excited about open silicon. This was back in fall of 2022, right before Tiny Tapeout had actually launched. And I taught this through CMU's student-taught course program as sort of a one-unit seminar. They have a program where any student can teach a one-unit seminar sort of thing. And it just so happened that this coincided with the launch of Tiny Tapeout. And students were interested, so we got some funding together, had these students submit to Tiny Tapeout for their final project for this seminar. And this turned out to be incredibly exciting. We had a bunch of students that would have never thought about actually taking a silicon design class who suddenly got a chance to tape something out and actually get silicon back that they had designed completely themselves of their own choice. And this raised a lot of interest in kind of, can we use this to get students excited about and interested in chip design? So the course we've had more than 60 students at this point go through this course across 4 semesters. First time was very experimental, and we got every single student to tape out at least something by the end of the course. In the subsequent semester, we scaled up the size of the course and scaled up the project requirements, and we actually taped out our own chip rather than relying on Tiny Tapeout. So that chip is our own custom multi-project multiplexer with all of the student projects included. We ran it again in fall. We got 13 students, and now we're trying to scale this up to a full 4-credit, full-sized departmental course. All the students in the course currently are on track to tape out, and we've also added weekly labs to give students more of an intuition of how stuff works under the hood. And for the past 3 semesters, I've been teaching the course. They basically let me teach a course in the department despite being an undergrad, and now I'm working with some faculty to transition it over as I start to graduate. So what is our student demographic looks like? It turns out that we've actually had a very diverse demographic of students, especially since we didn't enforce a ton of prerequisite knowledge in the early iterations of the course. So we have our biggest demographic, or the most interesting one, is underclassmen ECE students, who are already planning on doing something in electrical computer engineering, but aren't necessarily sure whether they want to do chip design or architecture or software. And this is a way to give them a little bit of exposure to a tape out, let them play with the tools a little bit in a low stakes way, build a little project, and decide whether this is something they want to pursue further. We've also had students that have taken some of the more advanced VLSI classes. They've worked with the Cadence tools, they've worked with the Xilinx tools, but even for them, they've gotten value out of this by seeing how the tools work under the hood. Unlike necessarily with some of the industry tools, these tools being open and using open standards makes it a lot easier for students to play with the tools and sometimes even build their own extensions to the tools. And we've also had some non-ECE students who just come in to get an understanding of how everything works without necessarily diving too deep into it. And we've had several students from departments like physics and statistics that have actually come in and actually managed to tape out through visual editors and schematic editors, and some of them have even learned a little bit of Verilog as a result of this course. So how did we structure the course? So our core tenets of the course, we have 4 core tenets, obviously centered around a tape-out project. We have lectures that focus more on fundamentals and how stuff works. Labs are exploratory, play with the tools, figure out what they're doing, report back, and obviously we want students to have hands-on experience working with the hardware, so we provide them with FPGAs and other hardware they need for their projects. So center of the course is the tape-out project. We try to encourage students to keep a low or medium design complexity. We give them that same few thousand standard cells worth of area from Tiny Tape-Out, but their projects are entirely self-defined. We don't tell them what they should build. They get to choose their project. They get to choose how to architect it, which I think is a very unique learning experience compared to a lot of courses. Most university courses, you're given a sequence of assignments to do. There's always a correct answer. Giving students the choice to pick their own project and self-teach how what they're trying to build works, how to build it, and then go through and build it and debug it is a very different experience that they may not have had before. So as the course staff, we try to provide as much advice as possible on things like project architecture and verification, but at the end of the day, how they design their project and even a lot of choices around which tools they want to use, especially as part of their verification flow, is left up to the students. One cool thing is a lot of students end up putting this project on their resume. Since it's a self-built, self-designed project, it's a great talking point for resumes and interviews. Try to structure the project to keep students on track. So when the course starts, we have a 15-week semester. When the course starts, we introduce the project, give them a few weeks to brainstorm collaboratively. We have them submit a project proposal so we can look at their project scope. We have a project design milestone. This is, I think, the most important part of this project. It's very easy to jump into writing RTL and then hit some roadblock. So we force them to take a step back and design out their project on paper, design out their state machines, design out their system architecture, and we'll actually look at this and look at the viability of their architecture before they start to implement anything. We also have a verification milestones, kind of get students, make sure they've tested the functionality of their design before they start pushing it through the synthesis and routing flow. And then at the end of the semester, they turn in their final GDSs, which we then integrate and submit for tape-out. Lectures are focused on how the tools work, so we've had lectures on topics like synthesis processes, what optimizations there are, PNR algorithms, testing methodologies, and also just the history of these kinds of things and what's out there, what tools are out there. Try to avoid the lectures being too heavily focused on how to actually use the tools. That's meant to be more hands-on exploratory. Hardware-wise, we provide every student with a ULX3S FPGA. It's one of my favorite FPGA boards of all time. It's based on the Lattice ECP5, which has great support for Yosis and NextPNR with the open source toolchain, and enough logic cells that students can both use this to play with and learn how FPGA toolchains work, as well as use this as part of prototyping and testing their final project. Get a lot more comfortable with it once they've tested it in hardware. And then another very important part of the course is the weekly hands-on labs, where we give students real experience working with the tools. And our main goal here is that the labs you're not working towards building something, you're working towards learning how something works, doing experiments. So we give them guidance, we give them kind of, you want to try building these things. Beyond that, we let them explore open-endedly. And one of the things we've been experimenting with is verbal grading, where instead of having them submit some code or submit a write-up, we actually talk to each student individually, ask them a few questions about what their understanding of the process is. And that's worked really well for the smaller class, but it's open question, how do we scale this up to a class of 30 or 40 students? It's a lot easier for 10 students when we can talk to each of them during a lab session. But the main idea is, we really don't want this to just be do this, do this, do this, do this. We want them to play around, learn, and report back to us. And even we've actually learned a few things from what the students have discovered during these labs. An example of this is our synthesis lab, where we have them play around with different Yosis passes after each step, visualize the design, see what the different passes do across a few different designs, and synthesize designs in different configurations. And this really fun example of something that you wouldn't ordinarily see unless you're looking for it is both of these are just reduction ands, but the way you write them in your Verilog actually substantially influences what the critical path looks like. We can have it balanced or unbalanced, and this is a few characters different in the actual source code. This is something that a student discovered while playing around with this lab. Clock domain crossing, so another one of my favorites. We have them build a bunch of synchronizers that are subtly broken, like this one where we have them put two toggle flip-flops together on a edge detector, and since we're not properly synchronizing the clock, this becomes metastable. We have them press the button a bunch of times, realize that it's metastable, and you actually end up seeing that the two flip-flops actually put out different values eventually, despite them being driven by the same enable input. And this is where it kind of clicks what metastability actually is. Simulation, we have them use CocoaDB with Python, and we have them try to interface that with other Python libraries. So the assignment we gave them here was, here's a driver for WS2812, which is an LED strip. Write a CocoaDB test bench for it that will actually generate an image render of what's being displayed. So this is something that would be a lot harder to do with conventional tooling, but is super, super easy with CocoaDB and gives them both a little bit experience with communication protocols, a little bit experience with CocoaDB. SiliWiz and OpenLane, we've been using these great visualization tools that have come out of the Tiny Tapeout ecosystem. You can actually have them synthesize a design through different steps in OpenLane and see kind of, here's the tap cell insertion, here's the decap cell insertion, here is the power strap insertion, here is the global placement, here's the refined placement. After each step, they can render it in this 3D viewer and see what has happened during that step. Static timing analysis. So another very unique opportunity is with the fact that we have such standardized and open formats, we can have students build their own STA tool. So we actually give them the output of a design from Yosis, and we give them, here's the timing parameters for different standard cells, and we have them build an STA tool. We tell them, write an algorithm to find paths in the graph, find spanning paths, then find measure the timing for each path, and then given the parameters we've given, calculate setup and hold violations, and discuss how you would solve them. And so every single student has built a very small, couple hundred lines of Python static timing analysis tool, and they found this also very insightful. Design for test, we have them play with the scan chain and generate some test patterns, another interesting one. And then we've had a few other labs, but those were some of the most interesting ones, and especially the idea of having them build out tools, build out their own small versions of existing tools is a great way to build intuition. So over past 4 semesters, we've had 60 student tapeouts. We've tried both taping out through Tiny Tapeout and taping out within the class itself through ChipIgnite. Both have their ups and downs. Some of my favorite projects are, I had an I2C peripheral. A couple students have built motor controllers with integrated feedback loops. Someone built a trainable perceptron, a single perceptron, but it could be trained in the silicon. floating point units, different CPUs, some esoteric CPUs, some historic CPUs, some examples of projects. And then post-silicon, we give them a little bring-up PCB. So we provide the silicon, provide the voltage regulators, and provide an Arduino-compatible microcontroller that they can actually run their test vectors against. And we've had some success. So we've had several student projects that we've tested and are actually working. Some of these, a lot of students provided test benches in our standardized, we've created a debug interface format that students can build their test benches in. And we've had student test benches run on that. And we've some students that are still working on their post-silicon bring-up. Quickly, a couple of lessons that we've learned. One, getting all the software installed on student machines is hard. We're trying to figure this out. We've had to use Docker. We've had to use Nix for OpenLane, Conda, and then a lot of students have ARM Macs, which you can't just run a Linux VM on. So installation instructions has been something. And the other one is setting student expectations. Especially earlier on in the iterations of the course, students would come in with very ambitious ideas. And while I applaud the ambition and I applaud the excitement, it takes a lot longer than a lot of students may expect to build something completely from scratch. So try to make it clear to students, project complexity is something they should be scalable. They should start with something simple, and more time they have, the more they can scale it up. And then finally, yeah, have them start early, make sure they think about their projects before jumping into the RTL design, and give adequate time for synthesis. We had a couple of issues where Yosis would hit a false combinational loop, and this actually precluded a project from being synthesized onto the tape-out. Unfortunately, the student had waited until very late in the tape-out process, so we weren't able to get it fixed in time for tape-out. Yeah. And then, thank you. So reach out to me if you're interested in this or have any questions, and a lot of our course materials are available at that link.
That's fantastic, Anish. Really good to see. I'm sure there will be some questions. I have a first quick question, which is that how much could the students sort of just Google things and rely on the existing community for support and debugging versus kind of coming to you and the other people helping them with the course?
I think a lot of students have been able to use existing resources and existing communities. We've had students join the Tiny Tapeout Discord, get help there, get help from us. We want students to more explore the community, because students will intuitively jump to the TAs, jump to office hours if they need help with something. So try to encourage them and show them what communities are out there that they can learn from, which we're really excited about.
Yeah, and presumably they sort of interacted with them as well, so not only kind of asked questions, but perhaps helped other people as they learn things maybe.
Yeah, we're actually interested in can students go on to contribute back to the community after this?
Yeah, that's a good outcome. Quick question over here.
I've got one. So the cohort size was about 15. How many GTAs did you have? Was it just one instructor? How many GTAs?
So for the first couple of iterations of the course, it was just myself as the instructor and kind of running all the course support. It was a lot. For the future, we are aiming for one instructor plus 2 TAs.
And what was the contact, effectively the lab contact hours per week then?
So we do 80-minute lecture and then an 80-minute lab plus office hours and asynchronous support, especially towards the end.
Maybe shout your question out and I can repeat it.
I'm basically curious about the infrastructure. When you're going on your own rather than using Tiny Tapeout, what the advantages are if you're using an SoC, what the patterning is, how you're muxing the projects, and also basically how you're integrating everything. Is it automated or you stick it there like manual style?
The question is about tape-out, like chip infrastructure when you implement it, and then how you then go and put all the projects in the silicon die.
Yeah, whether they're using an SoC,
like
how they're muxing the projects.
Like Caravelle or your own custom thing kind of thing. Yeah.
Yeah, so for the first iteration, our system was relatively primitive. We put together our own MUX module and tiled everything and hooked it up to that with OpenLane. We did use Caravelle for the pad frame. This was thankfully after a lot of the Caravelle issues had been resolved. So we used Caravelle for the pad frame, custom little multiplexer with custom I/O chain to configure the multiplexing direction. For the current iteration of the course, we're looking into doing something a little more automated the way Tiny Tapeout does, where we can assign specific grid squares and have it build the multiplexer spine.
I have a question about the bring up. So you are doing the tape out, but clearly the chip is not going to be there on the same quarter or semester for doing the bring up. So how do you manage that part?
So that's actually been a bit challenging. So that is part of why we built this board. This is fully self-sufficient. You plug it into USB and you can flash it using the Arduino IDE and talk to your chips. So this is something that we can actually ship out to students after they're done with the course. We can't really force them to do bring up, but we can hand them this and tell them, run your test vectors against this, and we'd love to see your results. And then for students that have not graduated, we can actually have them come back, asynchronously work in the lab on bring up of their chips.
All right, Anish, I think that's time. Sorry, yeah, ask questions offline. Thanks again. Great presentation. Cheers.